Hello everyone, it's Dayu. I'm really happy to make my contributions for the first virtual European conference on fracture. And I'd like to see that it really makes sense to make discussion through some virtual events, just like this virtual conference, especially in this period. Okay, so let's go back to my topic. A cohesive-based method to replicate the effect of strain rate on RTM-6 epoxy resin in tension. The objective of this work is to propose a time-independent numerical method for strain rate effect on RTM-6 epoxy resin with cohesive elements. And during the modeling, we can have a better understanding of the fracture behavior of such polymer materials. The presentation will be start from the background, experimental activities, numerical methods, and something about the results. And finally, it's the conclusions and the further development of the proposed method. Let's first say something about the background of RTM-6 epoxy resin. As well known as one of the most typical thermoset polymers, RTM-6 epoxy resin has been widely used for composite materials as matrix. And such composite materials is widely used in aerospace industry, so it's really important to investigate the RTM-6 epoxy resin, especially the mechanical behaviors. The tensile behaviors of such materials has been reported, like Figure 1, in the literatures about which can be regarded as the typical curves and the different strain rates. And such tensile behaviors is not special for RTM-6 epoxy resin. It's also found for other polymer materials, just like PMMA, which has been shown in Figure 2. You can see that these two curves is kind of similar. And there is one more important interesting thing is that the defects in the polymer materials is really hard to be avoided, because it's not just this kind of defects is just not just including the voids as usual, but also something like the chemical reactions and also the function scattering. So it's really hard to be removed no matter what kind of manufacture process we are used. So this kind of defects is believed as one of the key reasons of the strain rate effect for such polymer materials. Then let's see something about the cohesive elements. The cohesive element is always used to model the interface, and as shown here, we can find that when we use the cohesive element, the delamination of the composite can be easily replicated. And also, the cohesive elements is widely used for the fracture behaviors. Besides all of this, when we change the cohesive elements material model, it can be used to model the materials containing the defect. As shown here, the red dashed line is used to model the material with defect. The last 2 points here is mainly used in present work. Regarding the experimental activities, the tensile test has been carried out in MST demo lab with an extremely small sample. Herein, we use a very small sample because it can help us to remove the effect of the voids for the polymer materials. This kind of strategy is very useful for the polymer materials. Also, we achieve a very high strain rate with the SHTP, the Spellis-Hopkinson tension bar. Besides, we use a high-speed camera to capture the fracture behaviors during loading, and also we use DSC technology to achieve an accurate measurement on the strains during the tests. I reported some experimental data here so that we can find some special phenomena. Firstly, the nonlinear behavior was found in the quasi-static test, but it has been reduced a lot for high strain rate cases. And also the modulus and yield stress keep increasing as the increase of the strain rate, but the failure strain decreased a lot. We use the numerical models just want to address why this can be happened. As for the numerical methods, I will first introduce something about the frame model. We just use the frame model to mimic the region, the central region of the gauge region of the real samples. From here, we can find something, and we use the shell elements to build the model, and the frame model was coupled by two parts. The first part is a normal shell element. With this, we only use the linear elastic material models, and both the modulus and Boson ratio came from the manufacturer data. Besides, we use the zero thickness cohesive elements because it's zero thickness and also it's a shell elements, so it's just like beam. It's a beam-like elements, and we use this to capture the behaviors of the RTM-6 epoxy resin and mimic the crack of this material. Maybe you are wondering why we use this kind of mesh, because it looks really ugly, and in the next slides I will explain something about that. From this, you can see that actually we have tried different kind of mesh. Maybe the most widely used one is this one because it's a regular mesh, but actually it's not suitable for our case, because if we use the regular mesh, actually we will regard the defect in the material is regular, which is really impossible. It should be generated randomly. So we use some arbitrary mesh methodologies, just like mesh A and mesh B, and we use this difference arbitrary mesh, but we can find that the results of the tensile behaviors is kind of similar. It's listed here. These two kind of mesh methodologies can give us kind of similar results. That means if the mesh is arbitrary, then the mesh methodology will have almost no effect on the results. So it's a good thing, but we use the mesh B is because we want our mesh methodology is arbitrary enough, which is better to replicate the crack path in our study. Okay, I will introduce something about the cohesive elements. Herein, we use two different cohesive material models. The type 1 is used to model the perfect materials, while the type 2 is used to model the defected elements. And both the tension and shear behaviors is replicated with these two with the same curves. And also, we have to give the parameters about under this rate GC and also the failure stress, which is the sigma F here, and the failure strain will be calculated automatically. Maybe you can see the difference between these two, and I will introduce something about difference between these two material models. For type 2, for the type 2, we can find that its failure strain is smaller than the type 1. That's because we know that if there are some defects, it makes the materials vulnerable, so it's easy to be failed. And besides this, we can find that for the type 2, the peak strain is come very quick than the type 1. So this is because we know that if there are some defects in the material, it will cause something like strain concentration. That makes the peak value of the strains come very quick. It's quicker than the perfect material model. Based on these two facts, the difference between type 1 and type 2 can be explained. And we have to note that herein we call it the defected cohesive model is not used to describe the behaviors of the defect itself, but we use this kind of material model to mimic the materials containing defects. And we didn't care about the amount of defect. We just use it to model the material with defects inside. And also, we use a very large sigma F, which is the failure strain, is because we want to mimic actually a perfect material for such for present work, but actually the perfect material is really hard to get. So we use the highest value that found from the literatures under different conditions. So we use this value. Besides all of this, we are using the implicit solver, because when we consider the strain rate inside, we have to use the time to control the strain rate, which means that we always use the explicit solver. But in this time, we remove the effect of strain rate and replace it by something like the defects and the proportion of the defects. So we can use the implicit solver this time, and it can save lots of time and with very high computational efficiency. And from here, we can find when we change the proportion of the defected cohesive elements in all cohesive elements, when we change it, the curves can change a lot, and the trend is kind of similar as the experimental data. You can see from here, and also this can give us some signs about that if we can just change the proportion of the defective cohesive elements and then let the results fit with the curves of the experiments, maybe we can also capture some phenomena during the tests and make comparison between that with the numerical results. So we did something like that. Firstly, let's see the case under quasi-static test. Firstly, we can find that the curves is good fitted with experimental data when the defect is 0%. Here, we said the 0% is not means that there is 0 defective cohesive elements, but we use only 1 defective cohesive elements in the frame model, and I put it in the center of the frame model. We just want to make the initiation of the crack. And with this, we can find that a very stable crack was found under the numerical model, both numerical model and the experiments. So it's a good way, and this can be validated then. And so let's move to the high strain rate. When the strain rate is equal to 270% and 70 per second, we can use the 40% of defective cohesive elements to model this case. And firstly, also we can find that the curves is good fitted with experimental data, and also there is one interesting phenomenon found in the experiments, that there is 2 cracks happened in the same time during the loading. In this way, this can be validated that maybe there are some defects that can be activated in the same time during the high strain rate loading. And with this, in the numerical models, we find that there is lots of crack happens, and I call it multi-cracks. The multi-cracks happens, and it can be shown in the experiments like some fragments flying out of the crack position, and this can be captured by the high-speed camera. This can also validate this case. For an extremely high strain rate, the 700 per second, the 90% of defective cohesive elements can be used to model this case. The curves can good fitted, and also through the high-speed camera, we capture lots of fragments from the crack position, and also the multi-cracks was happened in the numerical model, and in this way, this method can be validated. Okay, finally, let's move to the conclusions and further development. For the conclusions, firstly, the fitting of the experimental curves through tuning the proportion of defective cohesive elements shows that maybe there are more defects can be activated as the strain rates increased, leading to more cracks before the failure of the samples and the high strain rates as witnessed in the experiments. Also, as the amount of the defective cohesive elements increase, the strains and modulus both increase, while the failure strain reduced. This also in good agreement with the results from the experimental data, and the presence of the defects might be one of the key reasons of the strain rate effect for such polymer materials, because our method can be validated from both the phenomena and also the curves. Also, this makes our present methods make sense. About further development, I think maybe it's better to link the proportion of the defective elements to some physical parameters, maybe just like temperature or some other stuff, because this can give it a very scientific basic, and I think there should be some link between the defects and also some other factors. Also, I'd like to apply this method to more complex loading conditions and larger structures in order to check the capability of this method. Herein, I'd like to thank Italian Ministry of Education's support, and also all the experimental works was funded by the EU's Horizon 2020 program. Besides, I'd like to thank my colleagues in the Italian Research Council for their kindly providing the test materials. Finally, I'd also like to thank the Demo Lab of the Ghent University. It provides very good experimental setting ups for the dynamic tests and gets very reliable experimental data that make a very strong base for present work. Thank you so much for the listening, and also hope to meet you in the discussion. That's it. Bye.